Hello everyone and welcome back. So this time we are doing another problem and there's going to be a massive amount of algebra. Because look here, we're going to notice that there are no numbers here, none whatsoever, which means everything's going to be done algebraically. So what's it asking us to do? Well, what we have here is a circular cam and it rotates with a fixed point O with a constant angular velocity omega. We want to find the velocity of this follower rod, AB, as a function of the angle theta. So how are we going to do this? Well, we're going to set our coordinate x to be that distance from the origin, which does not move, to this point A, which does move. And we're going to relate x to the angular position theta. That's supposed to be a theta right there. And then finally, take some time derivatives to figure out the position relationship and between the angle and the velocity. Now, I'm not going to make you do this on your own. This is too crazy, but we're going to try it together. So let's jump right into this, okay? So first off, we got to make a relationship between x and that angle theta, which is not all that easy to do. Okay, that's not super easy to do. So first off, we can figure out what this distance d is, if we wanted to, from our origin to the center of the cam. And then we can figure out this distance right here from the center of the follower rod to the center of the cam. Now, why would we want that? Well, we'd want that because this value right here doesn't change. Okay, it doesn't change. At any particular point when they are connected, the distance between these 2 points will be stationary. And that helps us out here. That's one thing that does not change and makes it a little bit easier to solve things. Now, we have a second side right here, where this one right here will be d cosine of theta. Well, this one is going to be d sine of theta. So this distance right here will not change. This distance won't change. The only thing that will change is that angle, and so from that we can figure out how x will change. So, therefore, x is going to be equal to d cosine of theta, that's that side right there, plus this line right here, which is going to be equal to the hypotenuse squared minus the vertical section squared, all under the square root. So this is the hardest part of this problem, and I'm not going to do anything like this to you on an assessment. I'm not saying you won't have a problem like this on an assessment, I'm just not going to do this to you on an assessment. So we just had to figure out what this distance would be as a function of theta, and we've done that now. Then we take our time derivatives, which are monsters. Okay, these are absolute monsters. I'm not going to take the time right now to show you how to get these derivatives. It's just the chain rule. It's not too terrible when you take it in because of that, but it's definitely not fun. So we do our chain rule. We get the time derivative for the angular velocity. Sorry, between the position, the velocity, and a bunch of other things. And then we have to realize something. So we plug in everything we know, which is just replacing theta dot with our angular velocity omega. And knowing that any theta double dots which we saw, which I don't think we'll see any, we did not, we can then solve and say, well, this is the velocity as a function of theta. So it's crazy. We don't have any numbers, which makes it no fun. But this is how you get the answer. And the biggest thing I want you to get from this is simply how we set up this coordinate. We picked 2 points, one point that doesn't change, and we related it to a point that moves by figuring out some trigonometry and making a realization that this distance doesn't change and that distance doesn't change. So thank you for listening. I hope this helps you, and I will see you all next time. Have a wonderful day. Bye-bye.